Another theorem that we encounter early in our study of Calculus 1 is what's known as the intermediate value theorem. And what you'll find is a lot of these theorems, when you read them, the formal definitions of them, they're kind of, they sound confusing, but they're actually really very simple. And this is another example of that, where it's actually a very simple concept, even though the words might, sound confusing. So first we'll just read it. It says, suppose that f is continuous on the closed interval from a to b, and n is any number between f of a and f of b, where f of a does not equal f of b. Then there exists a number c in the open interval from a to b such that f of c equals n. So again, it's one of these, if-then type statements. The suppose part is the if part, and the then part is obviously the conclusion, right? So if you have that set up, that's there in the first sentence, then you can conclude what's in the second sentence. All right. So if you look, what I have here below is two graphs, and the first one is an example of the setup being satisfied, and the second one is an example of the setup not being satisfied. So let's see what the setup is. The setup says, suppose f is continuous on the closed interval from a to b. Well, if you just look at that blue graph there on the left, it looks like that's going to be continuous on negative infinity to infinity. But here we're just talking about a closed interval from a to b. So let's just take this point here, 0, let's say, I guess, right, to be a, and this point over here to be b. So there's my closed interval from a to b, and it's clearly continuous on that closed interval because I can draw the graph from there to there without having to pick up my pen. Okay, so it's continuous on the closed interval from a to b, and now they're saying let n be any number between f of a and f of b. Well, first things first, where's f of a and f of b? If this is a, then f of a is the value of the function at a, which is actually right down here. So this would be f of a, and if this is b, f of b is the value of the function at b. So it's right there. It's that y value, right? F of a and f of b are y values, whereas a and b are x values. Okay? So they're telling me that n is any number between f of a and f of b. So in other words, n is a y value that's somewhere between f of a and f of b. So let's say n is here. So there's my setup, right? N is a number between f of a and f of b. So what can I conclude? I can conclude that there exists a number c in the open interval from a to b such that f of c equals n. Well, in other words, where does this function take on the value n between a and b? This theorem guarantees that it has to happen at least once, right? There exists means at least one. Now, could there be more than one? Sure. But this theorem just guarantees that there's at least one. So in this case, actually, if you look, there's going to be one here, and one here. So in this case, there's actually 3 values of c. So I can call this one here, that's like my c1. This one here, that's my c2. And this one here, that would be my c3. So in this case, there's 3 numbers in the open interval from a to b such that f of c equals n. All right. And again, this theorem just makes sense if you think about it. Is there any possible way that I can get from here up to here without crossing this horizontal line? No, right? There's no way I can get from down here to up here as long as it's continuous without crossing that line at y equals n at least once. And in this case, it happens 3 times, right? So that's all intermediate value theorem is saying. Now, the idea is, though, this is only true for a continuous function, right? Because if you look at the graph on the right here, this looks like it's the graph of y equals 1 over x, right? So this thing is actually going to have a vertical asymptote at x equals 0. So in other words, there's an infinite discontinuity at 0. So you can see here how this intermediate value theorem is not going to be true in this case. Because let's say I have an a value here, and I have a b value here. Right? What's f of a? F of a is going to be right here, and f of b is going to be right here. But suppose I want to make my n be 0. Is there any c value in between a and b such that f of c equals 0? No, there isn't. Right? And the reason that there isn't is because this is not a continuous function. Right? So there's no c value between a and b that make f of c equal to 0 in this case, because the intermediate value theorem doesn't apply because it's not continuous at x equals 0. Right? So I can't apply the intermediate value theorem in this case because it's not continuous. Now, where else wouldn't it work? If there's like a jump, any kind of discontinuity. If there's like a jump discontinuity, right, the intermediate value theorem doesn't have to apply because it's not continuous. Or even if there's a removable discontinuity, it doesn't have to apply, right, because it's not a continuous function. Right? So I gave you the case of an infinite discontinuity, but it also wouldn't apply in the case of a jump discontinuity or a removable discontinuity. Okay? Now, realistically, where do the problems come from that deal with intermediate value theorem? They usually come in the form of things like this. They'll give you an equation maybe, and they'll say use the IVT to prove that the equation e to the x equals 3 minus 2x has a solution in the open interval from 0 to 1. Now you might look at this question and say, how the heck does this have to do with the intermediate value theorem, right? The intermediate value theorem deals with a function, and this is not a function, this is just an equation. Well, simple. I can very easily turn this equation into a function, right? What I can do is I can just get everything to one side, so I can subtract the 3 and add the 2x. So I can turn this equation into e to the x plus 2x minus 3 equals 0. So there's my new equation, and now what would I do? I would say, call that left-hand side of the equation f of x. So I'm going to say let f of x equal e to the x plus 2x minus 3. Now, the thing to note here is all this is the sum of an exponential function and a polynomial function, right? So f is continuous. It's continuous on negative infinity to infinity, right? It's continuous on all real numbers, but in particular, it's continuous on the closed interval from 0 to 1, right? In particular, it's continuous on the closed interval from 0 to 1. So now what am I going to do? I'm just going to evaluate it at 0 and 1, when I substitute 0 in for x, I get e to the 0, which is 1, plus 2 minus 3. Right? So I would have, 1 plus 0 minus 3. So I would have negative 2. And then when I substitute 1, I would have e plus 2 minus 3. So it's really e minus 1. And what is e minus 1? It's roughly 2.7 minus 1. So it's roughly 1.718, approximately. Right? So in other words, f of 0 is negative and f of 1 is positive. So what does this mean? This means by the intermediate value theorem, there must exist some c that's in the open interval from 0 to 1 such that f of c equals, well, if it was negative at 0 and positive at 1, there must be some c in between 0 and 1 that makes it actually equal to 0, right? Because if it went from a negative to a positive, 0 in particular is between a negative and a positive, right? So there must be some c in that interval such that f of c equals 0. So since this is the case, that original equation, e to the x equals 3 minus 2x, must have a solution in the open interval from 0 to 1. Right? So what did I do? I turned the equation into a function, noted that the function was continuous on the interval from 0 to 1, showed that at 0 the function was negative, and at 1 the function was positive. So if I apply the intermediate value theorem, I can say since it went from a negative to a positive, there had to be some value of c in between 0 and 1 that would make the function equal 0. So that meant that the original equation had a solution in the open interval from 0 to 1. All right? And again, you got to think about that. If the function went from being negative at 0 to positive at 1, and it's continuous, somewhere in the middle it had to actually cross 0. Right? It can't go from a negative to a positive without crossing 0. So there had to be some c in between 0 and 1 that would make it equal to 0. Okay? And again, I mean, that's really where majority of the questions from this section would come from.